This week, during the practicals, we will be putting all our attention towards multi-part objects, multi-part models, or models that are complicated in a certain way that there are some parts of the model that actually follow each other in terms of displacement. I know that may not sound very clear to you right now, but I will show you some examples which will explain the real meaning of what I want to tell you here by means of matching and non-matching meshes. Let's take, for example, a certain multi-object model. And some very simple examples are just, let's say, bimetallic strips. Yeah, we have at some point of time or other during studying physics, we have considered the use of bimetallic strips for making some kind of conductor, or for example, in an iron you also have a bimetallic strip, so you have differential heating coefficients for two metals that are in contact with each other, and depending upon the temperature, one of them is in contact, the other one can shrink and not be in contact, so it helps in creating certain mechanical connections because of an actuation of a temperature or something like that. Yeah, so for example, if we have a bimetallic strip which looks like this, so you have metal 1 and metal 2 in contact with each other, there are two different parts in a model, and this is a very simple model, so I've considered only a two-dimensional section of it. And if I want to place these two parts together in a finite element model, then physically, in terms of geometry, they are sharing this one edge. Yeah, and when they share this one edge, at this point they are connected to each other. And if you want to study the heat transfer coefficients of how the heat transfer is happening, how the stress is going to be changing across the metal interfaces, you want them to be in contact with each other and to be smooth. So what you do is you consider a mesh which is more or less uniform. So you kind of like try to make uniform mesh such that you have nodes which are also present at these interface locations. Yeah, so that means you have nodes here that are shared between the two parts. And this is a simple example of a matching mesh. I could also consider that I use these two different parts from two different models and they were already meshed beforehand, and then I put them together. And in that case, it could be that these two parts have meshes that do not match with each other. Yeah, for example, if I have a much finer mesh on this one than on this one, then you see that there is a node here while there is no matching or shared node on the other side. And this is an example of a non-matching mesh. That means the nodes are not overlapping. And generally, in finite element models which have multiple parts associated with them, it may sometimes be possible to have matching meshes, while most of the times it would not be possible to have matching meshes. Yeah? That means that there is a certain difficulty that we are facing. There's a challenge that if we have multiple parts in a certain model, to make it behave smoothly across interfaces, we'll have to make sure that we impose a condition which mimics the condition of having matching meshes. So in this case, I want to give you first examples of how you can create matching meshes in a commercial finite element package, and then following that, how do we think about non-matching meshes? How do we actually make that work? So let's first start with matching meshes. In a software such as Abacus, which is pretty modern software, what the advantages of this software is that you have a certain CAD model, and this CAD model can come from any generic CAD software. You can use CATIA, you can use Pro Engineering, you can use AutoCAD, and you can have so many more that can cater to the same CAD model. And you can develop these files in terms of step files, in terms of STL files, and all those different formats are possible. And these formats can be imported into Abaqus very easily. And these parts then therefore become geometry in Abaqus, and then you do the rest of the things as we have been doing after creating a geometry by means of a sketch. Okay. Now in Abaqus, when you have multiple parts that are imported into a certain model, you have to go into the assembly and create instances. And all these instances then have to be placed together in the correct way. So if there is a part which has to be moved on top of another part, then we have to make sure that physically we actually move it and place it in the correct location, etc. So they have to be placed together in the correct locations with respect to each other. And once that is done, we have to make sure that the mesh, it can be of two types, of course. You can have a dependent mesh, which means you meshed on the part, and you can have an independent mesh, which means that you have to mesh on the instance, that is after taking it into the assembly. So if, for example, you have a dependent mesh which is meshed on the part, all these parts before they become instances have already been meshed. You bring them together and you have to make sure that all the meshes at the interfaces are the same, right? So in terms of a dependent mesh, you have to make sure that the mesh matches. And that is very, very, very difficult task. So what you would rather go for is to go for an independent mesh, which means that you will mesh part in assembly. That means you're meshing the instance. And here you can use something called merge option to either merge the geometry or to merge the mesh. Now, what's very important to note is that in Abaqus, if you have used the option merge, then Abaqus creates a new instance related to a new part created back in part section of model. And that's a very, very bad situation, because you don't know what Abaqus took back with it and what it didn't. So most of the times, while Abaqus takes all the information with it, which means to a part when you merge it, you have properties associated, you have section assignments, you have orientations, but really it can happen that it does not take it back into the new part. If you use option such as merge, mesh, or geometry, then you can also lose the original parts. And that's again another serious problem that actually sort of makes me angry than sad, because I've worked very hard to create this model up to a point and then I lose everything and I don't know exactly what I lost. So although you can merge it, you also have to go about doing all the section and property assignments and orientation assignments most of the time all over again. So it's not a very good option. Although it can work sometimes, it's not a very good option. Then software such as Patra and Nastran are actually much easier to use in this case. Because what you do is that you have multiple parts, but they don't have to be assembled. You create parts as assembly directly. So it's your responsibility to put them together. You can work in groups. Yeah, we don't know what that is, but basically just parts that are put together in groups, and then you can put them together in a bigger model, etc. and then you mesh all at once by means of mesh seed. So you make sure that the mesh seed at the interacting edges is the same. So they have to be the same at interfaces. And then you can enforce same mesh or node locations. So therefore, what you need to basically do at the end is to use the option of equivalence under meshing, and you get rid of overlapping nodes, get rid of duplicate nodes, and make sure that you have the same mesh across interfaces.